Hey guys, Scallywag checking in, and welcome to the Renderer Performance Devlog. I haven't paid a great deal of attention to performance on this project, especially on the renderer, and so a lot of it's kind of slow. So a couple weeks ago, I set out to fix that. The first order of business before we do any programming is to set up a test scene and take some baseline measurements. So I decided to use this kind of sine wave terrain that I just had laying around. With LODs turned off and culling turned off, it generates about 10 million triangles and draws that with 2,500 draw calls and doesn't hit 60 FPS. So with a rough baseline in order, we can crack open Nsight and take a more detailed look at the GPU profile. So when we open up Nsight, we can see a few things right off the bat. The frame time is 24.2 milliseconds, which on this beefy laptop should be a lot quicker. The first two stages of the pipeline here just draw stuff into gbuffer textures, and they're quite slow. It's about 8 or 9 milliseconds to just do those draw calls, and that should be a lot quicker than it is. Another thing we can notice is that this shader stage right here is a Gaussian blur that does a blur on a lighting bloom texture, and it is also very slow. It's probably about 10 milliseconds for this shader to run, and 10 milliseconds for lighting bloom is not an acceptable amount of time, so we're going to take a look at getting that down as well. So the first thing that I did was to just trim down the amount of texture memory that the renderer was using. I was able to turn both the color and normal buffers down to 16-bit float, which halves those memory requirements, and I was also able to completely eliminate the position buffer by reconstructing the position from depth. This is a pretty cute trick. It takes a screen space X and Y and a depth value and then applies the inverse transforms that produce those to get the world space coordinate back. And it works pretty good. I do see a little bit of artifacting in the shadow mapping, and I would like to take a closer look at that at some point to see if I can get rid of that or at least minimize it. But for the most part, it works really well, and it eliminates an entire 32-bit texture from the gbuffer, which is a big win. So just those simple changes took us from about 8 or 9 milliseconds per frame for the gbuffer draw to 5, and that's a really good reduction for such a simple change. We're going to reduce that even further later on in the video by compressing the vertex data, but for now I'm going to move on to the dominant factor here, which is the blur for the lighting bloom. I decided to implement the bloom in one of the guest articles on learnopengl.com. It's from 2022, and it's titled Physically Based Bloom. So the idea with this algorithm is you downsample and then upsample, applying a light blur at each step, and this algorithm provides a remarkably good result for quite cheap. So the setup for this algorithm is pretty straightforward, as you might expect. You just make a bunch of textures and an FBO, and then you're off to the races. I won't go through all the code that makes this implementation work, but you can kind of imagine that the code that runs this is similarly simple. You just run through each of the textures in order, binding them to the FBO, and run the shaders. The shaders are available on the website that I mentioned, and even if you're not going to implement this, I recommend going and reading them because they're quite clever. So when we come back to Nsight over here to measure our progress, this is now our bloom filter, and as you can see, we went from a full 10 milliseconds down to just over a half a millisecond, which is almost a full 20x increase for just reducing the texture memory that our bloom filter is operating on. And that is just an absolutely enormous performance win. I am super happy with that. The last thing I wanted to do to improve GPU time was to compress the vertex data down to quite a bit smaller than it was before. You can see my vertex definition here, and it's a pretty chunky boy. We've got full 32-bit float v3s for vertex, position, normal, and color data, as well as a 32-bit float for transparency and emission. That works out to 44 bytes per vertex, and that is just way too much. I was able to get that down to about 10 bytes per vertex, which is pretty good savings, but I didn't actually get as much performance out of that as I was expecting. I actually had to make a new tool to measure GPU time in the in-game profiler, and it turns out that it did cut down the time to rasterize the G-buffer textures by about 20% or 1 millisecond, and that's enough to keep it in there. Unfortunately, it did add quite a bit of code complexity because I now have to maintain 2 discrete geometry buffer types, which is kind of annoying, so I might try and smooth that out in the future. So the last thing I wanted to take a minute to talk about was CPU performance. Now, I mentioned at the start of the video that it takes about 2,500 draw calls to render this scene. You can actually see the exact number. It's 2485 over here on the left. And that sounds like an unreasonably high number of draw calls, and it kind of is. But the thing that I wanted to mention that I was surprised about is if we pause the profile over here, this render draw list is what actually does those draw calls or dispatches those draw calls. And you can see that each one of them only takes like a millisecond or maybe even less. Like these sleeps are about a millisecond. This was a little mini one. I don't know what happened there. But point is that it's actually pretty fast. If we go and drill down a little bit and take a look at draw, we can open this functions window, and this shows you every invocation of that function across the run of the program. And you know, there's like one that's slow, but most of them are just like a couple hundred cycles, and that's pretty damn fast. So I just wanted to mention that because it surprised me how fast dispatching those draw calls is. Now, I don't know what happens in the driver once you dispatch those. It seems possible that the driver hogs an entire thread, or worst case, multiple, but the actual dispatch turns out to be surprisingly quick. So to wrap up, we started at over 20 milliseconds a frame, and we're ending at under 7. So that's a 3x improvement, over 3x improvement on frame time, and I'm pretty happy with that. I also did some extracurricular work, like I split the renderer out onto its own thread. I know I didn't talk about that, but it really didn't do much for performance, so I didn't think it was really relevant. I also changed the debug system architecture somewhat. It used to build to a DLL, and now it's just welded into the program. This just makes it a bit nicer to use, and you don't have to worry about having another DLL load at startup and things like this. The next thing I'm going to work on is a gameplay update, and so the next video should have some nice juicy visuals. In other news, I'm getting really annoyed with the video editing software that I'm using. The audio system, for some reason, introduces tons of popping, as you may have noticed into the audio. And so if anyone has recommendations for either cheap or free video software that I could use to edit these videos, I would be more than happy to give them a try if you let me know in the comments. Subscribe for more, and thanks for watching.